Mhm. So now we will learn about the real-time object detection pipeline. Okay, so far we learned about the object detection pipeline, which are RCNN stream algorithms, and last time we learned about the detection transformer, okay, DETR, which is the transformer-based approach. And in this lecture, we will learn about real-time object detection pipeline. I mean, YOLO version 1, we have learned is already real-time. Okay, so, but here we will review how YOLO, the advanced version of YOLO, which version 2 and 3 are improved uh, uh, from the YOLO version 1. Okay, and also we will learn about the RT-DETR, which is the real-time DETR. Okay, normally the transformer architecture, they are very slow to deal with. I mean, in the inference as well, DETR is very slow, but RT-DETR, they made it real time. So we will learn about which kind of techniques are used for that. Okay. This is the review slide. So we have learned about the two-stage method for the object detection. RCNN, we extract almost 2,000 object bounding boxes, and for each region, we apply the CNN. Okay, so we have to apply CNNs 2,000 times and classify those features extracted from each region to the class semantic classes. And by doing that, we can achieve the object detection. But this is slow, okay, almost taking 1 minute. And the accuracy is also limited. And fast RCNN, we for the fast RCNN, we apply one CNN operation to extract the two-dimensional features in the middle, and then attach these features instead of the images, and then apply the ROI pooling to make them in the fixed dimension, and then apply FC layers to map them to the object classes. Okay, that is the fast RCNN. And last, the faster RCNN, they are removing the bottlenecks in the object proposal algorithm. So previously it was obtained by the clustering algorithm, but now we are also estimating that object proposals. Okay, so we are making them more robust and also making them more efficient. Okay, so gradually these RCNN algorithms are getting faster by involving this type of modules, and also their accuracy is becoming more robust. Okay. And also last lecture, we have learned this DETR-based algorithm, and transformer-based algorithm, which is called as DETR. Okay. So here, basically, their input is image features. Okay, and those image features are added with spatial positional encoding, and they are becoming mapped to this value key query, okay, and then applied with the self-attention mechanism. And by applying, sorry, by applying few more layers, which is differentiable, we can get the encoder output, which is the improved features, okay? And in the object query, in the detection task, object detection task, I mentioned that this is some random vector in image domain because there are no sequential output in the image domain. We just randomly initialize these object queries, and then we anyways learn this random vector to maximize the training accuracy. So, but after training, this is remained as some vector which does not have any semantic meaning, but they are some helpful vectors that can minimize the training loss. Okay, anyways, we multiply the linear vector. We first apply the positional encoding on this, and then map them to the key query values, and first apply the self-attention mechanism, and then apply the cross attention by using their output as the query and using image feature as the value and key. We are doing the attention mechanism, and we call this as the cross attention. And by applying few more differentiable layers, we map them to class and bounding box information we are requiring for the object detection. That is the DTR architecture. But I mean, this type of architecture is very complex because, especially because of due to the attention mechanism. So actually, attention mechanism, their complexity, time complexity is order n scale. Okay, where the n denote the number of input. Okay, input tokens, number of input tokens, number of object queries, or number of image feature dimension. Those are input to the transformers. And actually, we are considering all the pairs of the input for the decoder and encoder. So, I mean, the attention mechanism, their time complexity is the n scale. So, transformer, their I mean, operation is not that efficient. Um, but I mean, we will start from YOLO again. Okay, so this is the first real-time object detector based on the CNN architecture, and we call that as actually the one-stage algorithm. And by in their title, they are saying their algorithm is you only look once, focusing, I mean, their algorithm is one-stage algorithm. And as I told you, they first divide the whole image into several grids. Here we are using 7x7 grid. And in each grid, we are estimating 2 bounding boxes and also estimate their class probability. And by applying NMS, non-maximal suppression algorithm afterwards, we are filtering out unnecessary bounding boxes. That's the YOLO algorithm. But as I told you, their algorithm is suffering from low recall, and also their localization error is higher than the RCNN-based algorithms. So this is also the slide I mentioned previously. So recall and precision, those two are very important measures for evaluating the object detector, but most of the algorithms nowadays are previous to YOLO. They are measuring only the precision when measuring the object detector. So recall is also very important to check whether the object detector, they are covering all the ground truths of the image. Okay, so when evaluating object detector, both are very important. But I mean, YOLO is more focused on this precision, whether their predictions are correct or not considering their predictions are covering all the ground truths. So sometimes, in that sense, YOLO is limiting, but later versions of the YOLO, they are trying to improve their precision at the same time their recall. Okay. One basic limitation of the YOLO algorithm is they are only estimating 98 boxes. So basically, they are estimating 2 bounding boxes per each grid, and there are 7x7, which is 49 bounding grid, and they estimate 2 bounding boxes for each grid. So there are only this number of 98 number of bounding boxes estimated from the YOLO version 1. But I mean, if there are more than 100 objects, okay, so they are basically, I mean, miss the object, okay, if there are many objects. And because of this small number, I mean, even though there are not many objects, the YOLO suffers from the low recall. So YOLO version 2 was proposed in later year, and as far as I remember, the next year, YOLO version 2 have been proposed, and uh, their I mean accuracy is greatly improved compared to the YOLO version 2. And at the same time, here the recall is not reported, but recall is also improved a lot. So this is the schemes that YOLO does not have, but YOLO version 2 is having these kind of schemes. So I will explain that one by one. But most of things are not that fancy, but they are some, I mean, implementation details. But anyways, they are helpful for improving the performance. So, I mean, in that sense, I think it's worth seeing. Okay. And one of the important changes is batch normalization. But I mean, this batch normalization is not something that this YOLO version 2 proposed, but at this year's where YOLO 2 has been proposed around that years, I mean, this batch normalization has been introduced in normal CNNs, which does the image classification as well. But YOLO version 2, they are trying to involve this batch normalization in their architecture as well, and report that their accuracy for the object detection is also improved thanks to this batch normalization. I mean, so using the batch normalization, they are reporting that their MAP, the precision is slightly improved. And I will explain what is this batch normalization. So batch normalization is actually the scheme that try to solve this type of covariate shift problem. This problem means uh, this is the CNN architecture. And if this is some distribution of the responses, okay, CNN response, how to say, their scales. This distribution is denoting their response, their scales. And after applying one fully connected layer or CNN layers, uh, their responses, their scales are transformed. Okay, but I mean their mean values are greatly, how to say, changes from the input when getting the output. Okay, we cannot control this type of things. Okay, in normal CNNs, and also after another layer, their distributions for the responses is also becoming a lot changed. Okay, we call this problem as the covariate shift. Okay, so data distribution for each layer, the responses, their scales are changing a lot. Okay, that's the problem. And sometimes this makes the CNN hard to be converged. Okay. So the batch normalization, their idea is uh, they want to normalize their scales in the responses. Okay. They want to normalize their scales, the responses, their scales. And this paper, batch normalization, their original paper is insisting that by normalizing their responses and normalizing their scales, they can stabilize their training. Okay. So CNNs now uh, doesn't care about the scales of their responses, but instead they are focusing on their, how to say, their values. Okay, they can more focused on their responses values. Okay, so what they do is uh, this xi means the layer's response. Okay, and they first compute the mean of the responses and also compute the variance of each layer's response. Okay. And then what they do is they normalize those responses by subtracting the mean and by dividing them using the variance. Okay. Then this is the obtained response that is Gaussian normalized. Okay. Maybe they will have mean 0 and variance 1. Okay. So they are following the standard normal distribution. Okay. So by normalizing all the responses after each CNN or FC layer, they are applying this type of operation to normalize their scales. Okay. And they are insisting that by normalizing their scales, the CNNs no more focus on their scales rather than they can focus on their more semantic values, and it can help CNNs converge fast. Okay, but one thing is, I mean, during training, they are obtaining these mean values of the responses for mini batches. Okay. So, I mean, during training, we are using n number of images simultaneously, and n is normally, this number of images. Okay. So at the training, we have this number of images and process these images simultaneously, and also use this number of images to get their mean values and variance. Okay. But the problem is during the inference, we we had to make the CNN work only for the one sample. Are you guys understanding this? During training, we can use multiple images together, right? But during inference, we have to make our network works for one sample as well. Okay, are you guys following this? In that case, we don't have, samples, enough samples to get mean value and also the variance, together, okay? So we need more than 2 samples to get their mean or to get their variance, okay? But during the inference, uh, if we process multiple samples together, we can get some multiple samples to get mean and variance, but inference have to also work for one sample. And in that case, it is hard to, we cannot get mean and variance. Okay, variance will be 0 and mean is just that sample's value. Okay. So that was the problem for this type of implementation. And their idea is like this. During the training, they also learn two more variables. Okay, they actually learn this gamma and beta, which can inversely normalize each sample. Okay, so I mean, uh, so thanks to these two variables, that is also estimated during the inference step, they can also learn, they can apply inverse normalization for just one sample. Before explaining about this, I have to explain this. So, uh, okay. Okay, yeah. So, thanks to this inverse normalization, even for the one sample, we can do inference. Okay, so that is the story. Okay, here, and thanks to this, without batch normalization, uh, the test accuracy is becoming unstable during the early iterations of the training. But you can see the blue curve is the network that is trained with the batch normalization. And in the early training epochs, that is also producing very good accuracy. So it is meaning that with the batch normalization, your network is converging faster than the network which is trained without the batch normalization. Okay. So the effect of batch normalization is already proven effective for the image classification task. But this is also showing, in YOLO version 2, they also test their effectiveness in the object detection pipeline and also find that it is also working in covariate, to solve the covariate shift, okay, and makes the responses, their distribution more stable and make the overall object detector converge faster than before, okay. And another, in here, using the batch normalization, the precision is slightly improved, okay? And also the other scheme is high resolution classifier. This is also very, simple things, okay? So YOLO version 1, they are training their, how to say, architecture. They use their backbone network from the VGG16 architecture, which was first used as proposed as the image classifier. Okay, we already see this VGG16 network, but they are pre-trained on the ImageNet data, which is image classification data, and also their image resolution was 2 to 4 by 2 to 4 when they are originally trained. But YOLO version 1, they are using this architecture whose original input was 2 to 4 by 2 to 4. But they just increased their YOLO version 1, their input size is 448 by 448. Okay. They are just using the same architecture, which is trained on 2 to 4 by 2 to 4 images as the feature extractor for these sized images. Okay, so somehow they are saying that this VGG16 network is not optimal for the larger size images where this YOLO version 1 will use. So YOLO version 2, their idea is they fine tune the original classification network, which was originally trained for this smaller image size, fine-tune the network to these resolutional images for 10 epochs. Okay, so they are wanting to make their image classifier, image feature extractor, more tuned for their own image size. Okay, are you guys following this? This is not a very difficult thing. Okay. And by doing that, actually, actually their precision is improved this amount, almost full. And also, maybe, uh, okay. So this is visualizing that image classifier pre-trained on VGG, pre-trained on ImageNet is using this amount of this dimensional images as input. So this was the ImageNet, their resized input, and they are mapped to this dimensional probability vector because ImageNet is having 1,000 dimensional semantic classes. So this was the the VGG16 architecture that was used for ImageNet classification task. But here we are using those architecture for YOLO output 7 bytes that is outputting this dimensional output. but using the same dimensional feature extractor, but using different 448 by 448 dimensional input. So we are anyways fine-tuning this architecture to these dimensional images to make them more fine-tuned to these higher resolutional images. And another thing is basically, I mean, the pooling layers are uh, proposed to reduce the response size. Okay. So when we use the pooling, 2x2 pooling, we can reduce the image size, the response size by 2 times. Okay. But also when we use the convolutional layers with stride 2, we can also reduce the dimension of the responses. Okay. So you already know about this. So pooling, when applying pooling, for example, max pooling, we are picking the maximum values in each 2x2 sized window. So the resultant output is halved compared to the input image. And also convolutions, if we use the stride as 2, then that is also, their dimension is also halved. Okay. But thing is, pooling, we are somehow losing our information. Okay. But convolutions, we are anyways transforming our original input to other format. Okay. So somehow their motivation is they can retain some missing information that may loosen, they may lost via the pooling layer, and they want to replace that using the convolutional layers and wanting to retain, I mean, possibly lost information. Okay, so they replace the pooling layers towards the convolutional layers. Okay. And also they removed the FC layers, which was originally in the YOLO version 1. They are wanting to process the two-dimensional signals rather than processing those in with the one-dimensional format. Okay, because basically we are dealing with 2D images, so processing 2D images using convolution operation is better. Not, I mean, rather than flattening them into one-dimensional signal and applying the FC layers later. So they are involving more convolutional layers rather than FC layer or pooling layers. Okay? That's their motivation. And by doing that, they can also slightly, I mean, by doing this, their MAPs are slightly reduced. Okay. And also, uh, ah, not this one. I mean, but here the accuracy is reported for these two. Okay, so I mean, after adding convolutions and after adding the anchor boxes, their precision is slightly reduced. But thing is, I will explain this later. But their recall is getting improved from 42 to, as far as I remember, 48, 47. Okay. So anyways, their recall is improved. I mean, at the cost of this reducement of the precision. Okay. So anyways, you will see later, but by adding convolutions, we can, I mean, retain more information compared to the FC layer or the pooling layer. And later, I also explain about these anchor boxes. Okay. So anchor boxes are here now. Okay, so this is the schemes that can increase the number of bounding boxes info estimation. Okay, so as I told before, I mean YOLO version 1, they are estimating only this number of bounding boxes. Okay, that is the main reason why YOLO version 1 was suffering from low recall. Okay, but using the anchor box scheme, they are actually wanting to increase the recall of the YOLO version 2. Okay, and when they are using 448 by 448 dimensional images as the input to the YOLO version 2, their intermediate functions, their convolutional layers and pooling layers are, tend to reducing their two-dimensional dimension by number of 32. Okay, so when they apply their internal, layers, intermediate layers, they will get 14 by 14 feature maps. Okay, from this 448 by 448 dimensional 2D image, they may get 14 by 14 feature map. Okay, and what they did was, for each, rather than using the grid, they are interpreting one pixel in this 14 by 14 feature as the grid, as the unit to estimate, n bounding boxes. Okay, previously for each grid, we are estimating 2 bounding boxes. Okay, and there was 7 by 7 grid, so there are this number of bounding boxes estimated from the YOLO. But here there are 14 by 14 dimensional 2D feature map, and they are estimating actually 5 bounding boxes for each pixels. Okay, so you can expect much larger number of, already this 14 by 14 is around 200, and by multiplying 5 is almost 1,000. Okay, around 1,000 bounding boxes are estimated from the whole image. So compared to 1998 bounding boxes, this number of bounding boxes are almost 10 times larger in number. So they could raise the recall, but because there are trade-off between precision and recall, here, the precision are resultantly slightly reduced. Okay. And sometimes this makes you confused, but instead of using the original dimensional inputs, they are reducing this dimension to 416 by 416 because they just want to get odd number of feature map. Okay, so in their paper they are saying that they just want to make this feature map into odd number because in the center of this feature map there should be one pixel, because they want to secure the center pixel as one. But in 14 by 14 dimension, for example, when their width and height are even numbers, there are, there's no one pixel for the center, but they may have this type of 2 by 2 grid in the center. Okay, but their motivation to secure just one center pixel is most of the images are centering main object, in the center position. Are you guys understanding this? This is not that difficult thing, right? So most of our real world pictures, real world photograph, they are focusing on the main object in the center. We are capturing our photograph by centering the main object, okay? So they just want to secure one pixel in the middle to, properly estimate that main object, okay? So rather than having this type of 2 by 2, unit in the center position, if the even numbered box, there is no center pixel, right? in the center, there will be always 2 by 2 grid, but when the width and height, they are 13 by 13 and having this odd numbered width and height, there will be one center pixels. So because of that, they just want to reduce, I mean, this original width and height by 32, okay? Because in the middle of their, their middle CNNs, they are tend to, how to say, reduce their dimensions by 32 times. So if they deduct these 32 pixels in the input, then their intermediate feature map will have this 13 by 13 feature map, okay? So they can secure this one center pixel in their feature map. So that is what they are doing. So when using this anchor box scheme, they are deducting their width and height by 32. Okay. So I mean, in YOLO version 2, their paper, they are always changing their input dimension. So it is a bit confused, but I mean, please follow that carefully. Okay. Anyways, what they do is when using their anchor box, from this 13 by 13 feature map, for each feature map pixels, they are estimating 5 bounding boxes. Okay, so as a result, they can secure almost 1,000 number of bounding boxes from an image, and this can raise the recall of the YOLO. Okay. Okay, compared to this number of boxes in YOLO version 1, they can increase the, recall, but instead, because due to the trade-off between recall and precision, their precisions can be slightly reduced. So as far as I remember, in the paper, they are reported that MAP becomes slightly less by involving the anchor box scheme, right? But their recourse, which is not reported here, is increased from 81% to 88%. So that's why they are using this anchor box scheme. Okay. And I think in your slide, the order is slightly different, but this new network slide have to be there in this position. Sorry about that. Okay, I will re-upload the PDF material. This was originally in the later page, but have to be here. Okay. And also, as I told you, the YOLO version 1, they used VGG network, okay, as the backbone network. But they are proposing the new network, which is dedicated to this object detection task. So they are calling their backbone network as darknet 19. I don't know why their name is darknet, but anyways, they name their architecture backbone network as darknet. And their main idea is to use batch normalization in the middle of this darknet, okay? And here you can see there's not much FC layer, uh, but having the convolutions mainly, okay? Anyways, they train this darknet, uh, and by involving this darknet, they are saying actually they could improve the precisions as well, okay? So, but here they reported only the precision with multiple things, okay? So I will explain this later. They change their network and also use this type of buyers, okay, for the bounding boxes. So as I told you, they are saying that 5 bounding boxes will be estimated from each pixels of the feature map, right? But that 5 boxes previously in YOLO version 1, they estimate their low center position X and Y position and their box size, okay, and confidence value, they estimate that directly from the features, pixel features. But here, they want to somehow use some priors for the bounding box, their size. Okay. So maybe in the training data, so they are using some Pascal VOC or COCO dataset, which is a large scale object detection training data. And they first apply k-means clustering to the size of the bounding boxes. Okay. And they said k is equal to 5, which means by collecting all the bounding boxes from the training data, and they apply k-means clustering algorithm that we have learned, okay? And they somehow cluster the bounding box, their sizes, okay, their width and height. They apply the clustering algorithm, and they say that when their k values are 5, it has the good trade-off between recall and complexity of model. So they use k is equal to 5. Okay. Anyways, they use this k as 5, and they divide all the bounding boxes coming from the training data into 5 clusters, and find that decide their initial dimensions. So this is the example of their bounding box size. So they just having the priors for their width and height. And they now have the 5 representative values for the width and height. Okay. All the from the old spicing, all the training data, they decide 5 representative width and height for the bounding box. Okay. So now so this is the how to say, the width and height coming from the training data, their prior. And now what they do is, rather than estimating the low values for the width and height of the bounding box, they estimate their ratio, okay, compared to the prior. Okay. So this is meaning that, so starting from this PW and PH, they only estimate their ratio to this prior. Okay. So now this is the resultant bounding box size, but they are starting having these priors rather than estimating the low values. They are estimating their ratio, and that is actually more reliable in network training. So by using this scheme, they can also improve the precision. And also, this is the center. I mean, how to say, they this is the center of the bounding box, and this is the center for each grid, and they only estimate their residuals from the center values. Okay, so this is also location estimation method in YOLO version 2. Okay, and this is same for confidence values. Okay. So by using this new network and using the bounding box dimension prior and location prediction, okay, they can improve the precision a lot. Okay. So, but this is not that fancy method, as I told you, but they can implement well and improve the precision. And pass-through network, that is also important thing in object detection method. So this is the order of this slide was also slightly strange. So I adjusted in the revised material. So I will upload that in the Blackboard. Okay. The idea of pass-through layer is concatenate higher resolutional features with low resolutional features. So, this is the architecture, and what they do is, uh, normally there's no path like this. So for the last mapping, we only use these last layers features, but this pass-through layer is meaning that they are wanting to use previous layers feature, okay, by concatenating it somehow with the later features, okay. And this simple scheme improves 1% accuracy improvement. Okay. This is a pass-through layer. I mean, this is especially the computer vision researchers are finding that the multi-scale information is sometimes important for this object detection pipeline. So, for example, in the image, some humans are very big, but some humans can be very small. Okay, but sometimes these later features are more focused on the small object, but in the previous layers, features are more focused on the larger object. So by combining this type of multi-scale features, we can somehow discriminate this multi-scale object more efficiently. So that is actually the reason for this. Okay. And also, as I told you, multi-scale training, that is actually the efficient way to raise the performance of the object detector. So as I told you, original YOLO version 1 uses their input dimension as 448 by 448. But when using the anchor box scheme, YOLO version 2 normally uses this 416 by 416 dimensional image. But instead of using the fixed dimensional input image size, when using this multi-scale training, the YOLO version 2 is using multiple scaled images as input for the training. So they on purpose train the images resized to this 320 by 320 for only 10 batches, only 10 batches, and then resize their input to this dimension. And they are actually having 10 different multiscales, and they are changing. And you can see their difference is having this 32 because their feature map is reduced by 32 times. So they on purpose changing their dimensions by 32 amount. Okay, so next is this, and next is this, and next is this. So until it reaches here, they are adding this 32 and resizing their input size to different scales and train the network. So by doing this multi-scale training, they can also improve their performance. Okay, because this multi-scaleness is important for the object detection task. Okay. And after doing that, they also do inference using different sized input image. So it is meaning that after training the network using multi-scale training, they are do inference with different sized input image. Okay, so of course, if we use higher dimensional input image, their accuracy is becoming good, but their FPS, which means the speed, the frame per second, which means how many frames are processed per each second, is becoming slower. Okay, because they are using higher dimensional input image, then their speed is getting slower. Okay, but their accuracy is becoming better. This is natural thing. Okay. So after doing multi-scale training, we can actually also adjust the inference times, inference input image size, depending on the application. If we require high speed, then we can use middle level or lower level image size, okay, to secure the real time or high speed rather than the accuracy. But if we require higher accuracy, we can select this higher dimensional input. Okay. So this can also, during the inference, once we apply multi-scale training to obtain the model, we can also change the inference. At the inference time, we can also adjust the input image size. Okay. Okay, so by doing this simple thing, multi-scale, okay, they can also, I mean, improve their precisions. Okay, that is the YOLO YOLO version 2 compared to the YOLO. Okay, so I mean most of the things are heuristics, but I mean YOLO version 2 are becoming robust compared to the YOLO, and mainly I think as far as I see, this anchor box scheme is most important, but because the most important part of the problem lying in the YOLO version 1 was the low recall. So using this anchor box scheme, the YOLO version 2 can solve that problem. Okay? By increasing the number of bounding boxes, they can solve the low recall problem. Okay, maybe for some of you, this might not be very interesting because these are very heuristics. Okay. And later, we will also see YOLO version 3, and also we will also learn about this real-time DTR. Okay? Maybe for today, I think we have time for explaining about this YOLO version 3. Okay, so YOLO version 3, this is also the advanced version of YOLO. Okay, and I mean, it becomes slightly slower than YOLO version, previous YOLO version, YOLO and YOLO version 2, but it is designed to have more robust accuracy. YOLO version 3 that actually predict boxes at 3 different scales. As I told you, multi-scaleness is very important for object detector. So in images, object their size, even though their semantic classes are same, their scales, the object scales can be varied. So to capture them effectively, the model have to consider this multi-scaleness. Okay. So similar to the pass-through layer I have explained before, the YOLO version 3, they are having 3 different scales and capturing features from 3 different resolutions and concatenating them all and estimate the final predictions. Okay. And so here, what they do is they also have n by n dimensional grid or feature map, 2-dimensional feature map. And for each feature map, they are estimating 3 scale responses because they are having 3 different scaled pipeline. For each scale, they are estimating this number of information. So as far as I understand, this is the class probability, and this is the thing for bounding boxes. Okay, so they are estimating 4 bounding box offsets and also prediction for 80 classes. Okay, so and this is the I mean considering the 3 different scales. Okay. Uh, so this is the pipeline of YOLO version 3. Mainly, their architecture is developed considering this multi-scale needs. So this is the original input, and this is the CNN stream. The convolutional and I mean sequence of the convolutions are located here, and in the middle, they are getting arrows here, and also they are also getting the subsequent convolutional layers here, and getting the responses here, and continuing applying convolutions. And I mean, by doing that, they are actually estimating 3 different responses here. Okay. Are you guys following this? Okay, so I mean, this is showing the sequence of convolutions, but in the middle, they are having different passes and also estimating 3 different estimations in the middle. Okay, so in these 3 different estimations, they are assuming that they are having different scaled information. Okay, so I mean here they are having this dimensional 2D features, and this they are having this dimensional features, and here they are having this dimensional 13 by 13 dimensional grid, and here they are having 26 by 26 dimensional grid, and here they are having 52 by 52 dimensional grid. Okay, so and for each grid, they are estimating uh, uh, these things, bounding box information and class probability. Okay, and then they apply NMS to reduce to filter out unnecessary bounding boxes to get the final result. Okay, so anyways, their idea is to obtain many bounding boxes from the multi-scale features. Okay, that's the idea of YOLO version 3. And as a result, they can their speed is becoming slightly slower than previous YOLO, but their accuracy, their precision is becoming robust by considering the multi-scale needs. Okay, and also they compared to the YOLO version 2, they are using darknet 19, okay, which is the advanced version of VGG. But here, darknet, they are using YOLO version 3, they are using darknet 53, which is similar to ResNet 50. So here you can see in the middle of the network, they are having the residual connection. Okay, that's not their idea, but at the time of this YOLO version 3, the ResNet appeared, and I mean, the author of YOLO version 3, they become to know that this residual connection can reduce the vanishing gradient effect. So they use this residual connection in the middle and propose the darknet 53. Okay, use that as the YOLO version 3, their backbone architectures. Okay, and they are saying that this darknet 53, they I mean propose is better than uh, ResNet, having more layers, and also they have very good trade-off between FPS and this accuracy. So they are using this darknet instead of ResNet architectures. Okay, they are saying that this darknet is more suitable for the object detection pipeline. Hey, this is a very brief review for YOLO version 2 and YOLO version 3. I think this is, I mean, if you want to understand them in detail, that is very complicated. Even you have to see into their code, but I just want to deliver some concept of their idea, okay? So that's YOLO version 2 and YOLO version 3. That was the idea to improve YOLO version 1. And later, in next Monday, I will further introduce about this real-time DTR that made DTR into real-time object detector. Okay, and then we'll also continue our lecture on multimodal learning. Okay. Okay. Thank you, and let's finish lecture today. Thank you.
맞아요.
네.
그 명령어에 따라, 그 명령어를 변수가 어떻게 주는지에 따라가지고 하프 그 어큐러시가 좀 다르게 나오는데,
그래요.
네네.
그건 처음 듣는데.
그러면 그 명령어를 좀 잘 나오는 명령어를